How are we doing, lovely people? It's Coach Fran from TWHS-9 Math Department, here to give you some entertainment during our social distancing and continuing your education. So, if you remember kind of where we left off, way back when we were back in school, the dark ages, we were talking about a couple things. We talked about a couple ways to solve quadratics to find solutions. And your teachers and myself went through a couple different methods, but in particular, I'm pretty sure most people sat on and stuck with the quadratic equation. So we just plugged some numbers into the quadratic equation and find answers. Sometimes we'd find two for the most part. Now, how does that lead into what we're discussing now, into Unit 9? Well, where it's going to lead is that we're going to start talking about what do those numbers, those solutions, mean on a graph. If I were to show you what the picture is, could you find those solutions? Well, I'm here to tell you that you can. So I'm going to go through these notes with you guys, which these notes will also be available on your respective teachers' canvases, okay, as well as being linked into the Google Drive that they will also link and share with every single one of you. So we're going to not quickly, but briefly go through these notes, kind of just talking about how to graph these quadratics. Now, Coach Fran, hold on. You're asking me to graph. How am I going to graph if I don't have a graphing calculator like we have in classrooms? Well, you're in luck. Hopefully, most of you, if not all of you, have at least been introduced to some degree of Desmos. And this is going to really pretty much be our bread and butter going forward with how we're going to start graphing these equations. Okay, so if you have internet access, you have Desmos. And Desmos is pretty much going to give us everything we need as long as we type it in correctly. And we're just going to have to identify certain key features or key attributes of the graph. Okay, and we'll talk about that here in a little bit. So, starting this off, reintroducing you guys to standard form of a quadratic. All of us have talked about this in every single class. As a reminder, the standard form of a quadratic, I'm going to put it in purple, is y equals ax squared plus bx plus c. What we were used to last unit is we used these equations, and what we did was we identified three numbers. We identified the numbers a, b, and c, which is exactly what we're going to be doing today. Now, and just labeling some of the key parts and key features of this graph. So I'm going to change to green, and let's move on. So if you notice, these graphs look a little bit different from what we're used to. We're used to graphs just being a straight line. Well, obviously, these guys are not. Any quadratic equation is going to have a graph that is in this shape. The shape is represented in what we called a parabola, okay? A parabola is just the shape of these quadratics. So this graph here is a parabola, this is a parabola, and so on and so forth. Okay, all of these guys are parabolas. Okay. So now, let's talk about some important things. So if you notice here on this left example, I'm over here right now. This line that's drawn here is kind of an imaginary line that we can draw through any parabola. Now, it's a particular line. What kind of line is it? Ask yourself for a second. Hopefully you answered it's a straight line, which yes, it is. But in particular, it's a vertical line. And this vertical line is in a certain place on this parabola. You might hopefully notice that this vertical line is cutting this graph right down the middle. Whenever a line cuts something down the middle, and we have the exact same thing and the same amount on the other side, it's what we call something being symmetric. So that's exactly what we call this line, or this imaginary vertical line that we'll draw at times that cuts my graph in two. What we do is we call this an axis of symmetry. Now, looking at this, how many times does this axis of symmetry touch my parabola? So looking at this, you might ask yourself for an answer one time. And it's always going to touch one time, and in particular at this particular point. Okay? The point at which the point where an axis of symmetry crosses a parabola is called a vertex. Now, the reason why we use the name vertex is because the name vertex represents a change in direction. What I mean by that, let me change some color, is if I start on the left side of my graph, because we read a graph the same way we read a book, from left to right. Looking at this graph on the left, my graph here is going down. At the point of the vertex is where my graph changes direction. So all a vertex means is that's the point where my graph changes direction. Now, your axis of symmetry and your vertex are going to have a very important relationship where if you know one of them, you're going to know the other. So if you know the vertex, you know the axis of symmetry. If you know the axis of symmetry, you pretty much know most, if not all, of your vertex. Okay? And we'll talk about that, how that relationship kind of develops here in a couple minutes. Now, looking at the next example to the right, so I'm over here now. Ugly star, there we go. What are these 2 points here that I've highlighted? What's so special about my parabola crossing this coordinate plane? So now we're dealing with an actual x and y. What do you notice? Hopefully you answer that these are x-intercepts. Now, we've all heard the word x-intercept before. What we've also heard before is a solution to an equation. Okay? In particular, you got last unit. So this is really where last unit ties in, is this guy right here. An x-intercept actually has a couple of different synonyms or different names that mean the same thing, in particular 3. An x-intercept is what you guys have been finding, which is also known as a solution. What we've said way back in the day is they're also known as zeros of the function. And another word that you'll see used is something called roots. Now, these are 4 different words, but what you have to remember is that they all mean the same thing. It's just a different vocab term for each. Okay? It's just more of a vocab. So this is one thing that you really have to make sure that you're on top of and remembering those relationships. Because I could sit there and ask you, what's the x-intercept of this graph? And on the flip side, ask you, what's the zero of this graph? And hopefully you answer the exact same number. Because all I'm doing is checking, do you know the vocab? So, x-intercepts are also called zeros or roots. Or we call them solutions. Okay. Small space to write, bear with me. And that's all there is to it. If I give you a picture, I'm just going to be asking you guys, what's the axis of symmetry? Give me the equation, which I'll show you how to do in a little bit. I'm going to ask you, what's the coordinate of the vertex? And what are my x-intercepts? And so on and so forth. I might ask you, what's a y-intercept? Certain things about a graph that you can find through Desmos. So, these 2 parabolas in particular, these last 2 at the bottom, are slightly different. Both the same shape, both parabolas, but what's different is their orientation, or where are they opening. The one on the left here is open down. Now, if you look at it, the vertex is still here, but the vertex is in a different position, okay? The vertex, in this case, is the highest point on my graph. Hopefully you agree with me, because if you look at the arrows of the graph, they're both going downward for after that vertex. So in this case, what's a good word that we could use to represent my vertex if it's the highest point on the graph? Hopefully you said maximum, which is exactly right. My vertex is always the maximum of my graph, if my graph opens downward. Which is a relationship, okay, that you'll have to know. Now, on the flip side, what if I flipped that parabola upside down and made it open up? Where's my vertex now? Hopefully you answered at the bottom. So if maximum was the word we used for the highest point, what might be a good word to use for the lowest point? Hopefully you say minimum, because you'd be correct. So my vertex, in this case, is a minimum because it's at the bottom of my graph. If you look at it, where's my graph opening in this case? Oh, it's opening upward. We'll just say up. So which would be also something I ask you is, what is your vertex area? Is it a maximum or a minimum? Does it open up or open down? That's just a basic eye test. We can look at the graph and answer those questions with relative ease. Now, moving on to the next section, what we're also talking about is, how do I find that equation of axis of symmetry? If I give you some equation, how could I find the equation of that line? Because every line has an equation. Now, what you're going to have to kind of use is dig back way into your brain and think about two little acronyms that we've talked about. In particular, look at what kind of line the axis of symmetry is. It's a vertical line, okay? Keep in mind, this axis of symmetry is a vertical line. Okay, I'm going to highlight that. It's important. Let's pick orange. So in this case, what is an acronym that we've talked about a vertical line? I know, at least in my class, we've talked about these two acronyms, VUX and HOI. VUX stands for a vertical line. X tells you what kind of equation it is. It's X equals. If it was horizontal, it would be Y equals. Okay, really, that's a 0 for those of you that know this. So since the axis of symmetry is vertical, the equation for that line is always going to be X equals. Now, if you actually wanted to find the line, okay, you can find it two ways. You can find the equation by using numbers from the equation itself given to you and plug them in. Or something else that's a little bit easier is understanding the axis of symmetry, if it's a vertical line, always touches the vertex. And one thing I know we've talked in my classes, vertical lines, what they share and what makes them special is that all of the points on a vertical line have the exact same X value, which is why they're X equals equations. So that's the nice relationship between the axis of symmetry and the vertex. Is the axis of symmetry in particular it's the same as the X value of your vertex. So really, when you find the vertex on your graph, you also know the axis of symmetry, which is a really nice thing. It's a good little note to make. So, and like I said, what value in particular did I say that we're talking about? The X, it's the same as the X value of our vertex. Okay. So, how do I find the vertex? Relatively simple. We need to find the lowest or the highest point on my graph. which we can do. Obviously, if it's lowest, what we just talked about is if my graph opens upward. That's my lowest point. And then highest would mean my graph opens downward. And that's how we would find that vertex. Lowest point would be here. Highest point would be here. And that's how I find that, where this is going to be some point x comma y. And this is some point x comma y. And so once you find that x value, you know what the axis of symmetry is. If the x value of my vertex was 2 comma something, my axis of symmetry is x equals 2. Okay, and you'll see that kind of in the next 2 examples that we'll talk about. So now I'm going to kind of split screen off for a second so I can type this in and also cover a material at the same time. So give me a second while I split screen this over. What is this? Close that. Okay, we're going to cover this. Boom. Look how fancy that is. Okay. So now all I'm going to do is I'm going to go to Desmos and I'm going to type in the equation for number 1. So y equals 2x. What is going on? Equals, here we go, 2x squared. So we need to put a little bracket, the little up arrow thingy, and then put a space, and then minus 8x. So minus 8x. Don't know why it's capitalized. There we go. So let's bring this into focus. So what's nice about this is my Desmos highlights a couple key points that I'm going to use. Okay. So let's answer my notes from top to bottom. Which way does this graph open? Hopefully you answered with relative ease that this opens up. Okay. Good color that I'll use here is I'm going to use blue. Okay. So it opens up. It opens. Yes, I know. It opens up. Now, I'm going to copy really as many of the points as I can read on my graph on my actual picture here, so I can copy and paste that. So it opens up. Where's my vertex? Well, my vertex is at the lowest point of this graph since it opens up. And that graph is 2, -8. So 2 and -8. So 1, 2, 3, 4, 5, 6, 7, 8. There's my vertex. What I also see, and I'm going to fill that out, and really, we're going to stop right here. If I know the vertex, what else do I know? Like I talked about up here. I also know the axis of symmetry. And how do I know it? It's because it's the same as the value of our vertex, the x value in particular. So what was the x value of my vertex? 2. And my axis of symmetry is always x equals in that number. So what I also know that now is there's a vertical line going through 2. And I'm just going to draw that line as best as I can. You can use a different color if you want. It doesn't really matter. Okay. So I know that this line is going to cut my parabola nicely and perfectly in 2. So I should see the same picture on the left as I do on the right. Okay. So y-intercept, looking at my graph, what's the y-intercept here on my Desmos? Hopefully your answer is 0, 0. That's where this graph is crossing, also known as the origin. What's nice about the origin is it's not only just the y-intercept, but it's also an x-intercept at this point. Now I do also have another x-intercept, which is 4, 0, which is highlighted on my Desmos as well. So I'm going to plot those points. And what you might notice here, which is something that should always happen, is every point on one side of my line is the same distance from the axis of symmetry as the point on the opposite side. What I mean by that is looking at 0, 0, it's 1, 2 points away from that axis of symmetry. So on the flip side of that, I have another point on that same line 2 points away as well. So these guys are symmetric. They're equidistant from that axis of symmetry. Okay? So you should always have 2 points on every horizontal line. If I were to draw a horizontal line, I should see 2 points going through that on the same line. And they should both be the same distance away from that axis of symmetry. Just a nice way to check. Now, I'm actually going to put these in orange. It pops up a lot nicer. D and R. What do you think those mean? Well, it stands for domain and range. Domain of every quadratic. So looking at this guy here on the left, okay, is it ever stopping? Answer is no. Okay, so domain is x values. Just keep in mind, domain is x's. Range is talking about my y's. My graph is infinitely going out to the left and to the right. Okay, so if I kind of get, can I get another point here pretty decently? Looking at my Desmos, it looks like I have a point at 1, -6. And then, which means I have another point on the opposite side at 4, -6. So my graph is doing this, drawing this on my notes. It's going infinitely. So since it's going infinitely, and a nice thing to always remember about a quadratic is the domain is always the same thing. It's always all real numbers, or that weird R with 2 vertical lines through it. Okay. All real numbers. The reason why is because this graph is going infinitely and slowly and slowly and slowly out to the right, and slowly and slowly out to the left, and there's no x value that's excluded from that. So it's eventually going to touch every single possible x value on this coordinate plane. Now, looking at the range, though, there is a particular boundary here. If you look at it, my graph's infinitely going up, so it's never going to stop going this way. It's never going to stop. However, is there a lowest point on this graph? Hopefully your answer is yes. The lowest point on this graph would be here. Which is my vertex. Now, being that my range is y, okay, I need to write a y. Now, what would be a good inequality that I could write that would represent that all of my points on this graph are above this vertex? Because if you look at the line, after my vertex, every other point on this line is going up, so it's greater than it. So, I just said it. It's greater than, but it could also be equal to it, because everything here is a solid line, and everything is going to be equal to in regards to domain and range, which makes my life simple. Okay. Since everything's greater than that, what is that y value there? What is that lowest point? Well, it was at -8. That was that y value. Now, a nice relationship to always, really to help you remember, should you want to remember this, is that the y value I use, didn't change it to highlight, the y value I use is always going to be the y value of your vertex. It's a nice little relationship that you can always use to check. Because like we talked about, my vertex is always my highest or lowest point, which means that y value has to come into play with my range, not my x value. And I'm sure most of you guys have seen this little trick with your teacher in regards to the inequality. And Coach Fran, how could I remember the inequality? Like, I might get confused. Well, here's a good little tip to help you out. I'll pick a light blue. So for that inequality, the direction of it is dependent on which way my graph opens. So if my graph opens up, it's going to open to the left. If it opens down, it's going to open to the right. Now, in my class, I know we've talked about the little trick. You can remember this because if something opens up and opens to the right, it makes the letter P for up. If it opens down It opens to the right, which makes the letter D for down. Nice little thing to help you remember. Makes those things easier for us. Okay. But really, other than that, that's about it. Might seem like a lot, but really it wasn't, just because I'm talking my way through it and giving you guys some things to look at. So let's go through number 2 a little faster. And delete this guy. Let's type it in. So I'm at y equals negative x, where's that little caret? Power of 2 minus 4x minus 4. So boom, there's my graph. Color really doesn't matter. Like I said in Desmos, if you want to change the color, you can go ahead and do that. Whatever you guys want to do. So here, bring it into focus. So this guy, just by reading it, it opens down. My vertex is at negative 2, 0. So I'm going to draw that point. Which means if I know the vertex, what else do I know? The axis of symmetry. And the axis of symmetry is always x equals, and the number is always the x value of that vertex. That's where I find it. So I know that there's some line. I'm going to increase the thickness a little bit. There's some line cutting this graph in two right there. Now, does this graph have a y-intercept? Going to Desmos? Yes, it does, at 0, negative 4. Does it have an x-intercept? Yes, it does, at negative 2, 0. Well, in this case, Coach Fran, it only has one x-intercept. That's okay. Okay, and you might notice, where did negative 2, 0 also pop up on this graph? Oh, it was my vertex. Sometimes your vertex will be the x-intercept, which is okay. So if I had a point there, looking at my graph, my eyes are going to my Desmos right now. I also have if I had a point at 0, negative 4, looking right across from that, I have one at negative 4, negative 4, because it needs to be symmetric. So like I said, plot as many points as you can see. Me looking at this, just going to finish up plotting. It looks like to the left and to the right of my vertex, I have a point at negative 3, negative 1. And negative 1, negative 1. Good. So my picture looks pretty close to that one, I like to think. Yeah, pretty good. So, finishing this out, the domain is always all real numbers. Like I said, and this guy is always. Okay. The range in this case, I have a highest value, and like we talked about, which means I opened down. So that really tells me what my inequality is going to be. It's going to be y is less than or equal to, and what was the y value of that vertex? It was 0. Like I said, that's a great little kind of pro tip to always help you remember that relationship. Okay. Well, ladies and gentlemen, that is it for me, going over this little introduction to key features of a quadratic from standard form. This information is going to be posted on your teacher's Canvas, which is accessible to a Google Drive. Should you need anything, please make sure that you reference your teacher's office hours, which they will be letting you guys know of. I know for me personally, that I'm going to be having a online conference with a lot of my kids. Not talking with them, but it's going to be a tutorial session where I'm going over some examples with them. So please be on the lookout for that. If any of you guys have any questions, like I said, please refer to your respective teachers. Thank you guys for watching this video and taking your time out of your day to learn this material. Please make sure that you are looking at the Google form that's connected with this. It should also be in the folder. That will be your homework that links this for you to complete and refer back to your teacher. If you need any other help with it, any other examples, please ask your teacher and they can provide you whatever materials you guys need. But thank you guys again for sticking with me and sharing this with me. This is new for all of us. Hopefully you like this. If not, don't know how to help you there. But hang in there. We'll get through it. And hopefully I will see all of you soon. Thank you guys. Have a great day.